So, okay, welcome back, and let us continue about antennas. Before that, I'd like to first mention a little bit more about different types of the waves. So we already have told that we have long waves, we have short waves, ultra short waves. What are their differences? So the difference is how these waves propagate relative to the surface of the ground and atmosphere. Yes. So long waves can actually travel across the entire planet, yes, across the horizon, and basically be always parallel to the surface without reflecting and anything like that. Medium waves can reflect out of the ionosphere. Short waves reflected both by ionosphere and Earth surface, and ultra-short waves can pass through ionosphere. So basically these four types are accordingly these different techniques of transmitting data over the long distance. So here is another video. This is quite short also, but it has two parts. So this is part 2, and here in recommended you can actually see the part 1 as well. So we will not watch it now completely. I just want to mention some moments. So first of all, the long waves. Yes, if we have here, for example, one radio station, here another radio station, then long waves will actually travel around the Earth's surface. You already know that the Earth's surface is not flat, yes? So long waves are actually capable of basically diffracting this surface, yes? Medium waves don't have this property good enough, so they are transmitted over the long distance by reflecting from ionosphere. So this is the way how we can transmit them. Otherwise, short waves can be used to reflect both from ionosphere and from Earth's surface over the long distance. This is also the possibility, but this is not so good because in these reflections we lose some energy naturally. Yes, not all energy is also reflected. Part of it goes to the space. Yes, so it's not as long distance as it could be with the ionosphere. And also the height of this layer from which we are reflecting is changing because ionosphere has different layers, as you may know. Yes, and accordingly, depending on frequency, these signals can reflect from different layers. And finally, ultra short waves can pass through ionosphere, and actually in that case we need a special artificial reflector, which is a satellite. Yes, basically for that purpose the satellite receives our signals and then redirects it to some another region on the Earth so that it's actually received. Now these ultra short waves with so high frequencies and so forth, yes, can actually also be transmitted over long distance in direct line of sight. However, in order to being able to transmit this over longer distances, we need to actually have enough height for each of these antennas, yes, and this is shown in this video further. So let us travel, yes, because if our antennas will not be high enough, the horizon can actually prevent this signal from going, yes, and basically this will not receive. It will be in blind spot, like we can say, and will not receive the signal. So for that matter, we need to have this height of antennas considering this curve radius of the planet high enough to being able to receive signal. There are some calculations also made, yes, and so on. So you can also familiarize yourself with this video as well as the first part, which more or less describes this direct line of sight and wavelength also. Yes, or you can see that, for example, we can use lambda divided by 4 as well. It's not always like we have to use lambda divided by 2. Okay, but let's go further. Now we are going to talk about these antennas. What types of antennas are there and how do we use them? So first of all, the antenna itself is an electrical device which is needed to convert current, yes, current into radio wave, into electromagnetical wave, and vice versa. This is based on electromagnetical induction principle. Yes, so basically, electromagnetical wave induces into this antenna, which is conductor, metallical part. Yes, some current, which we can work further, and vice versa. When we send some current into this antenna, it induces electromagnetical wave, which is then transmitted further. So the antennas can be different. We can have receiving antennas, we can have transmitting antennas, so basically the antenna which can work only in one direction, and we can have combined antennas which are capable both of receiving and transmitting signals. So the principle is quite simple, which I already described, is that the current is actually making magnetical field. This magnetical field induces an electrical field, magnetical field again induced by electrical field, and so forth and so forth. And this forms the direction of the radio wave, and somewhere eventually we'll have second antenna around which magnetical field will induce some current, and this current will be received as a signal by our receiver. So this is the idea. Electrical field and magnetical field are actually in orthogonal planes, yes. So we can have, for example, horizontal plane as a magnetic field and a vertical plane as the electric field, yes. Also, they have different phase, and that's their principle. Of course, we cannot really work with it if the frequency is 0, yes, because direct current does not induce magnetical field. So we are talking about only alternating current, AC current, or harmonical oscillations, more or less, yes. So what kinds of antennas are there? Basically, there are 3 large categories. So we can have linear antennas, which basically are just some metallical parts. We can have antenna array, which is basically multiple linear antennas, yes. And we can have reflector antennas, which have this dish-like part, yes, which is called a mirror or reflector. So let us discuss each of these types in more details a little bit, how it's working. So for linear antenna is basically very similar to a simple resonance contour for which this capacitor is like wide open. Yes, we can consider that we have actually opened it, and so the magnetic field, which usually is between this capacitor plates, yes, is now instead free to leave, yes, and induce according to electrical, magnetical, and so on and so forth current. So basically we send alternating current, and this alternating current produces magnetical field. This size of this metallical part is actually related to wavelength. Yes, for example, lambda divided by 2, lambda divided by 4, lambda divided by 10. However, as it has also been mentioned in previous video, especially if we are having many antennas, such as a MIMO case, it's very important to use this wavelength. Yes. Not wavelength, but the length of the antenna related to the half of the wavelength of the signal. And of course, for that, we need to use appropriate signal frequency, yes, because as you have already mentioned from our first lecture, this wavelength can be actually in kilometers. So it's not really usable for us. Yes, we can use it only if the size of the wavelength is such that it actually enables us to make such physical dimensions of the antenna. Okay. So Of course, we can make even greater antennas, such as 10 lambda, for example, and that will be even better for energy efficiency. And that's why usually some TV centers, some radio centers have these large spires, yes, as antennas, to actually increase the coverage of the coverage radius of this radio station and allow multiple people to receive their signal. This is actually also related to this fact, yes, that we need to consider that the Earth is not flat and that horizon can prevent from receiving this signal. So that's serving two purposes. We increase the height for the greater coverage, and we use longer antenna to actually be more energy efficient, to increase the power of the transmitted signal. So for simplest antenna, which is called dipole, yes, and which is displayed here accordingly, consisting of two metallurgical parts, the direction in which the signal is transmitted is not actually isotropic. So isotropic means that we have this in center some source of the signal, and the radio waves are being transmitted in all directions equally, forming a sphere. Yes, basically like this air balloon, representing the with its surface the electromagnetical wave. Yes, and as if in the center there is the transmitter. In reality, energy distribution is a little bit different. So we have still here our antenna, and the radio wave goes in the horizontal plane, more or less, yes, rather than vertical. It doesn't go upside or downside. So this is horizontal dipole, and also there can be vertical dipole. Of course, you can rotate this picture so that it will go up and down as well. So not in all directions. So dipole radiation pattern is not uniform. It's not in all directions, yes. Actually, we can see this demo on YouTube channel, how it looks like. Yes, by following that link in presentation. So this is our dipole antenna, and this is where the radio wave is propagating. So if we watch from upside and from the just side, we can see these patterns, yes, that radio waves are actually propagating in certain direction. Well, for our purposes, this is usually good enough, yes, considering that we don't need to send signal in space anyway, yes, and well, if we need to receive signal from space, then we can actually physically orient this antenna in either direction, so we'll be able to actually receive it from any direction we want. But this is still something we need to remember, that this pattern is somewhat limited. Yes, it's not omnidirectional. So let's go further. So this is rather simple antenna, basically just single metallurgical part. Yes, we can go further and make more advanced antennas called antenna arrays. So basically, we are using multiple dipole antennas combined together into one antenna array. And this enables us shaping this pattern. Yes, so sometimes, for example, in mobile communications, when we have this base station, we have this cell in which this base station operates, and it's common practice to use sector antennas working in multiple sectors. So, for example, one antenna will only work in this sector, another antenna will work in this sector, and another antenna will work accordingly in this sector. So this way we can repeat some frequencies, so it's efficient, yes. And well, if you will have this course on mobile communications, then probably you will that will be one of the first things that you will learn about frequency reuse principle. And one of these principles implies that we use these sector antennas. And for that reason, we need to make certain that actually signal is prevented from going in this direction in order to not make interference. And therefore, we need to actually shape this radiation pattern into a desired form. This is, again, very similar to this air balloon, which you can, shape by compressing in certain points, yes, to make a desired form. And this is actually a very good analogy, because what happens is that the energy that was previously here will now be converted and put into here. So basically, the total energy, like the amount of the air inside this balloon, is just redistributed. So we can put all that energy we don't need in this direction to actually make stronger signal here. And this is actually very convenient and very effective. Furthermore, we can have here components called phase shifters, which changes the phase of the current and accordingly change this pattern electronically, meaning that, for example, if we'd like to, we can make it, for example, like this or like this. So we can avoid the need to climb this tower and tilt this antenna mechanically. Yes, we can instead change some currents, and this antenna will act as if it has been rotated physically. So by using this approach, we can actually form this radiation pattern on the go by changing these signals. So this is actually also very nice thing. Yes, and the simplest antenna array actually is just a television antenna, which is used for receiving different channels. Yes, it's called logarithmical periodical antenna because, well, each of these stems actually has its length changed according to certain logarithmical law. Yes, and basically this way we can receive different frequencies at the same time. This radiation pattern accordingly is directed, yes, meaning that you need to rotate this antenna in certain direction in order to be able to receive signal correctly. So, yes. And similarly, it works for mobile communications, yes. You may have seen LTE towers, antennas, they are like these shaped antennas. So that's what is actually inside of this case are multiple dipole antennas. So which each of them is single dipole antenna. Yes. And you can have different sized dipole antennas inside. So here we can see that they are all equal, similar. Yes. But some of them can be smaller, some of them can be bigger. Yes. And this way it will be possible to work with different frequencies. And again, there is some circuit underneath this panel, yes, and by changing some currents and some controlling signals, it's possible to shape the radiation pattern to transmit signal into desired direction. So, yes, this is the modern antenna approach. And this will also be used for 5G, for MIMO antennas, and so on and so forth. So basically, we rarely use these simple dipole antennas just by themselves. We are now using rather, how to name it, antenna arrays. This also includes some radars and some military antennas as well to find location of some targets and so on and so forth. But the idea is quite rather simple. We use multiple dipole antennas. Of course, you need to calculate everything correctly. You need to have correct spacing in between them. You need to send correct currents with correct phases. But this can be done electronically. So no need to actually climb and rotate this antenna all the time. Now, for the reflector antenna, here we go even further and we shape this pattern into even more condensed beam. Yes, so now it's very similar to laser beam. And again, all the energy that otherwise would for dipole antenna be there now is concentrated inside this beam. So this is very high power beam, concentrating all the energy, yes, which allows sending these data over the very large directions. So the main idea is that the receiver or transmitter is located in the focus of this mirror, yes, and then the received signal reflects of this focus and concentrates at this point. So basically, and vice versa. If this is a transmitter, actually it transmits signal and it's then sent as a focused beam. Yes, so it creates a very narrow radiation pattern, literally a single beam, which is requires very precise rotation of the antenna. So if you have some experience with satellite television, you may know that you need to actually face the satellite dish antenna into right direction of the satellite in order to be able to see these satellite channels in the television. Yes, and if you want to switch to another satellite, then you have to go out to rotate this antenna, and again you will see. Of course, you can put multiple receivers, yes, here as well, working with different frequencies. And you can have multiple antennas too. You can have 2-dish antennas, 3, and so forth. Even it is possible, as it's done for radio telescopes, for example, to have these servo motors rotating this antenna according to some computer program calculations. But this is, well, some advanced method. And this is the demonstration how this energy pattern is formed. Again, you can open this video. There is no some sound description or nothing like that. So at the center here, at the focus, we have this transmitter sending waves in all directions. But this mirror then focuses the energy into this direction, yes, so that most of the energy goes into horizontal direction. Yes, so that's the idea of this mirror antenna. So, okay, so I believe that for today we have covered everything that we wanted. Do you have any questions? So, no, I cannot see any questions in chat either. Okay, then today it's all, and the next week we will have 2 lectures and we'll continue working on our course project, because we will discuss some information theory, some coding, and we'll be able to actually make some more calculations for your course project. So thank you for attention today, and as usual, I will check all the works you have sent me. If you have more to send, you can send me more. And thank you and goodbye.